cardinalities. So here's a list of some sets with different cardinalities. There's a set of size, there's all the J, J0, J1, J2. These are all the finite sets, right? But then we also have the natural numbers, which happen to be the same cardinality as Q, right? So this is the same cardinality as Q. They're in the same category. But then there's also the real numbers, which is not in the same category. Okay? Interesting. So there's a natural question you should ask yourself. Are there other sets of different cardinalities? Are there other things here? There's a question. Interesting. Here's a theorem. So the answer is yes, there are in fact tons of different cardinalities. In fact, there are an infinite number of cardinalities. Is that countable or uncountable? It's uncountable. There's a lot of cardinalities, and here's a theorem. So for any set A, the claim is A cannot be put into one-to-one correspondence with 2 to the A, where the power set of A. What's the power set of A? The power set of A is a set of all subsets. 2 to the A is just a notation for the set of all subsets of A. And this is a theorem which you should try to prove it. I claim it actually uses a very nice argument. This argument here we used for the rationals can be reused here. Proof, it's a diagonalization argument. And I'd like you to try to think about this, and then I might tell you next time how you prove this. But it looks very similar. It's this is called the Cantor diagonalization argument. And if you think this is somehow a bit surprising, you should know that it actually was a huge shock to mathematicians of the late 1800s when Cantor came up with his argument. People really scratched their heads and said, "What? Really? There are different sizes to infinite sets?" Yes, there are. And so the consequence of this particular fact is that, if you look at the set of all functions or graphs in the plane, set of all functions from R to R, that's a much larger size of infinite set than the real numbers, okay? Because it's basically a power set of the real numbers. So you can just keep going if you want. One other thing I should mention, I'll just mention this, is there is a question of whether there's a size of infinity in between n and r. You could ask that question. And it turns out that that question is is provably undecidable. Okay? So what does that mean? It means is you could take it to be the answer to that question to be true or false, and not violate the mathematics as we know it, unless mathematics itself has some inconsistency. Okay, so it's a rather surprising fact. That's called the continuum hypothesis. Okay, we'll see you next time.